Today we're going to talk about rotational inertia and angular momentum. But to start, let's review what inertia is. Inertia is the object's tendency to stay in the state of motion that it's currently in. It resists change in motion, and inertia is measured by mass. Well, rotational inertia is an object's tendency to resist change in rotation. So if an object is not rotating, something with a lot of rotational inertia it'd be difficult to get that object rotating, and likewise it'd be difficult to stop that object from rotating. Now, inertia is measured by mass, regular inertia. Rotational inertia is measured by where the mass is located. If mass is located closer to the center of the object, it has less rotational inertia. If mass is located farther from the center of the object, it has, or I should say the center of rotation, it has more rotational inertia. So the teacher has 2 meter sticks with clamps on them, and if you were to take each meter stick in your hand and hold it above your head and rotate it like helicopter blades, you'd notice that the bar that has the clamps very close to the center, that particular one is easy to get it rotating, and it's also easy to stop it rotating. That one has a small amount of rotational inertia, where the one that has the clamps farther away, that one is hard to get it rotating. It's also hard to stop it from rotating. And so we say that that one has more rotational inertia. It's not measured by mass. They both have the same mass, but it's rather measured by where the mass is located. So here I have a picture of the description that I was giving you. This one at the bottom has less rotational inertia, and the top one has more. I would highly suggest that you grab the meter sticks at some point today and you give it a try so that you can feel what it is like to have more rotational versus less rotational inertia. Now, when I come back tomorrow, we'll go through this derby where we're going to predict who wins in a race. But the idea is if you start 2 objects from rest at the top of a ramp, neither one is rotating. And the object that gets to the bottom of the ramp first is going to be the one that is more likely to start rotating sooner. And so an object with less rotational inertia is going to actually start rotating more easily and thus get down the ramp first and win the race. When we have moving objects, that object has momentum. When we have objects that are moving in circles or rotating, we have angular momentum. Now, the equation for linear momentum was mass times velocity, but remember, mass is how we measure inertia. So linear momentum equals inertia times velocity. Angular momentum equals inertia times velocity, but I want rotational inertia, which I just described, times rotational velocity, which is frequency. Now, we have a law called the conservation of momentum, and the conservation of linear momentum says momentum is conserved unless an outside net force acts on an object. And then we have an impulse, we change the momentum. Angular momentum is conserved unless an outside net torque acts on an object. So in order to change something's angular momentum, there has to be an overall torque on the object. So if you have something that's spinning and you want to change the rate of spinning, you want to change its rotational velocity or frequency, how many times around per second, there are 2 ways to do that. One, you can exert a net torque on it, which will change its angular momentum. And so if the angular momentum goes up, the rotational velocity goes up. So think about a spinning wheel. If you were to spin it with a little more force, you just exerted a net torque, it got more angular momentum, it's now going faster. But the cool thing about angular momentum is if you don't exert any sort of torque on it, it will maintain its angular momentum, but you can still change its rotational velocity if you change its rotational inertia. In other words, if you change where the mass is, then you can actually change how fast the object's spinning. So there's 4 videos I'd like you to click on and take a look at them, but I want you to look at when the athletes are spinning, when they tuck or they bring their arms in, or however that they change their body position, they'll be spinning at a certain rate, and then when they bring their arms and legs in and tuck themselves, they'll be spinning much faster. Now, they're not changing their angular momentum at all. They're changing where their mass is located. They're changing their rotational inertia. And so if they decrease their rotational inertia, they're going to increase their rotational velocity, and vice versa. So check out all 4 of those videos that show some great examples of changing rotational inertia and then changing your rotational velocity. The last video that you watch is figure skating, and so then you can go through these questions when you're ready. So as the figure skater pulls her arms in, what happens to the angular velocity? She spins faster. It increases. As she pulls her arms in, what happens to her rotational inertia? It decreases. More mass is close to the center. As she pulls her arms in, what happens to her angular momentum? Well, nothing. There was no net torque exerted on her, so her angular momentum did not change. So if we have a spinning wheel, we know that it has angular momentum because if it's spinning, it definitely has momentum. It's called angular momentum. But where does it get that angular momentum? Well, I probably grabbed the side of it, or you did, and spun it. And so we exerted a force through some distance. We exerted a torque. And that net torque was enough to change its angular momentum, give it some angular momentum. And by exerting a force through some distance, we did work on it, and we gave it some energy. The type of energy that we gave it is a type of kinetic energy called rotational kinetic energy.